Hello everybody and welcome to the last video in Chapter 8, Bond Enthalpy. We will be calculating later on in thermochemistry and thermodynamics an exact way of figuring out the bond enthalpy or the change in enthalpy for a reaction. Right now we're going to do a calculation based on just looking at what bonds are broken versus what bonds are formed during a reaction. So the change in enthalpy per mole, we're going to be calculating how much it's going to take to break a particular bond of a substance. So for example, here's an equation, and we have CH4, which looks like this. And it is going to react with chlorine gas. So if you draw out the Lewis structures of these, it makes it a little bit easier to see the changes that happen. And then we have a new bond here between the chlorine and the carbon. And a new bond between one of the hydrogens and the chlorines. So we want to know what the change in enthalpy will be when we have bonds broken and new bonds formed. So here we're going to lose and break apart a carbon-hydrogen bond, and we're also going to break apart the chlorine bond. So when this happens, there's going to be some sort of energy required to break these bonds between these elements. But on the product side, the formation of these new bonds will release energy. Now, depending on the value of energy needed to be put into the reaction and the release of energy will determine whether or not our enthalpy is positive or negative, which will also in turn tell us whether or not we have a endothermic or exothermic reaction. In this reaction, we have one chlorine-hydrogen bond and one chlorine-chlorine bond broken. And we have one chlorine carbon bond and one hydrogen chlorine bond formed. What we need to do to find the change in the enthalpy of a reaction is we take the sum of all of the enthalpies of the bonds broken. So this here is from the reactants. And we subtract the sum of all of the enthalpy of the bonds formed. This is from the products. And just a note here that this is the opposite of Hess's law, where the change in the enthalpy of reaction is the change in enthalpy of the products minus the change in enthalpy of reactants. We will discuss Hess's law in chapter 5 and 19. So looking at the reaction again, we need to know the individual enthalpy values for all of the different types of bonds. So if we take a look here, the change in enthalpy, we have 413. Well, this here is the value from that CH bond that broke. And this here is the value of the Cl-Cl bond that was broken. Now we're going to subtract what was formed, and this will be the carbon-chlorine bond formed, and then this one must be the hydrogen-chlorine bond. So you must be given these average bond enthalpy changes in order to do this. So once we know, we can do the math, and I'm sorry about writing over that, but this ends up being negative 104 kilojoules per mole, where if we used Hess's law or if we looked it up in a book, the actual change is negative 99.8. So for an estimate, it's a really good way of figuring out the change in enthalpy of the reaction. What's important for you to note is if you look above, taking two of the single bonds of carbon does not equal the same as the amount of the enthalpy in one double bond between two carbons. So you need to be given each type of bond If there's a bond, single bond between two elements, and you need a double bond, you need the value for the double bond. Here is a more visual look. The reactants start here at this level of energy and is increased up in energy. Energy is taken in order to break the carbon-hydrogen chlorine-chlorine bond. And you'll get this CH3 plus H plus 2 single chlorines atoms. That is not a Cl2 gas. Those are individual chlorine atoms. This is in an intermediate state. This is where things are broken apart and getting ready to recombine and rearrange to form the new products. And when the new products are formed, there's going to be a release of energy to form the chlorine, carbon, and the hydrogen chlorine bonds. The difference between the initial energy and the final energy, that is our delta H of the reaction. So remember to keep in mind that our delta H of reaction is the sum of the hydrogen bonds broken, and this is from the reactants, because the reactants will have bonds that are broken, and the H bonds formed are the bonds that are formed from the product side. This completes our discussion of Chapter 8. The next chapter in our unit will be Chapter 9, where we will be studying the molecular geometries of compounds and looking at some other bonding theories.